So we're given a question, X of a kind in a deck of cards. In a deck of cards, each card has integer written on it. Return true if and only if you choose X greater than equal to 2. That is it possible to split the entire deck into one or more groups of cards, where each group has exactly X cards and all the cards in each group have the same integer. So let's move on to the test case first and realize what is actually happening. 1, 2, and 3, 4, 4, and this is 3, this is 2, this is 1, right? This is the case. So what are we actually doing is the basic opportunity that or basic observation that I could make out was all the cards in each would have the same integer. So let's try to hash these same integers which are occurring. So I've hashed it like 1 is consists of 2, 2 consists of 2, 3 consists of 2, and 4 consists of 2, right? So possible partitions could be of 2, could be of 2, could be of 2, could be of 2, right? If instead of two twos we would have the number of twos would have been more, like suppose let's just say if we try to modify this array and add two more twos, right? The number of fours would have been 4, right? But still the answer would have been 2 because uh, if you just go through the conditions, each group has exactly X cards. So the X card is basically GCD or the high HCF of all these counts, as you can see, as you can observe, which is happening. If we have added another 2, then the value of 2 would have been 5, but we are not able to, but since the value is 5, we are not able to do a partition of 2 as well because 5 is present and it would just not satisfy these particular conditions. So yeah, this is the question that we were talking about. So unordered map, we try to do it, uh, we are trying to use unordered map, and this is a map, and what we are trying to do is the entire deck, we go iterating throughout the deck. So we are incrementing the occurrences of MPI. Once we are received with all those possible values, what we are doing is we are iterating throughout the map, and we are actually trying to find int answer equals to 1. Answer will be equal to GCD function, same name, GCD function, right? ID dot second and value answer, right? And we try to get the answer. So it's all basically there are some questions which are like we're able to observe the pattern, and I think this particular question was one of them. I think okay, it's not working because uh, oh, so we're not required to answer it. Like so, if answer return answer is greater than equal to 2, then of course we can call it that it's a function. So okay, what happened is 1 2 3 4 3 2 1. What did the answer come? Like what was the answer? Like can you just see out the answer? Output is false. Output is CDIO is 1. Why is this 1? Because second answer equal to GCD of answer. Okay, so if we take 1, 1, okay, so HCF will be 2, right? Okay, so this should not be the case, right? Answer should be uh, first value should be different. First value should not be 1, of course, because then the HCF would be 1. In this particular case, you can see that okay, what can we do is we can just simply Either we try to assign it, and after assigning it, we just change it, right? So try to first assign it. If answer equal to -1, then answer equal to it dot second, and after that, else else yeah, I think this will work. So let's try to submit it. Let's see if it works or not. Yeah, it's working fine, and just the way we expected. So we move on to the next question, which is counting of primes. So counting of primes is a question which is based on sieve over Eratosthenes. So let's try to implement and see what is actually sieve over Eratosthenes. So there is this major algorithm which is used to it was a sieve, it was a table which was compiled by Eratosthenes and all. So see the history part of it. So I tried to talk about what this table consisted of. It table used to calculate all the prime numbers which are present. Here we'll be trying to do the same thing. So suppose this is 0, this is 1, 2, 3, 4, 5, and so on. We're going to do that. Let's try to do till 10. So as you can, so we used to mark initially all of them are right. So if you know about this, you must know that we used to mark these. Initially, we try to assume that all these are not prime number. All these are basically prime numbers. We try to assume this fact. Then we try to mark 0 and 1 as not prime, not prime. After this, we go to 2. So when we go to 2 and we call it that this is a prime number. So for int I is equal to 2. If it is a prime number, if it is not marked, then we mark the rest of its multiples of 2 as not prime. They have not been divided. So 12 would be also cut off, something like that. Then we move on to the next one and we see that 3 is also not marked. So 3 is not marked, hence we consider it as a prime and we mark the rest of its uh, you know multiples, and we do repeat the entire process. And after that, those which are left, which are not marked, can be considered as the prime numbers because they haven't been. If they would have been composite number, they would have been marked earlier by their some of their factors. But since like 2, 3, 5, 7, 11, these are that type of numbers which haven't been marked, we consider them as the total numbers. So what we can do, simply we can have vector int size of the vector. We can just call it SOE as the overactive thinness. We can call it a size as N0. That's it. And after that, what we can do in order to know have better memory optimization instead of integer, we can have bool because we are only dealing with boolean values, and so we're considering first that all of them are prime. Then what we do is we mark bool of 0 equals to false and bool of 1 also as false. Done. What we can do is after that, right, is equal to I less than Okay, so here you should be aware of this fact that we are only concerned till the value of square root of n. Why? Because as you know, to calculate the prime numbers, you would have agreed with this fact that we are only concerned till the point where I cross I is less than equal to n. So the same condition applies over here also. Int I is equal to 2 cross I, that will be the first multiple of that particular number, and what we can do is it should have a condition. If SOE of I is equal to true, right? True, then we can do this in a different variable. Then j less than equal to n, j plus equal to I, as that will be the next multiple, and SOE of I would be equal to false, and that's it. After that, what we try to do for int I is equal to 2, I less than equal to n, I less than I cross I. In fact, what we can do is I cross I is equal to n I plus plus, or it should be like similarly like this. It should be like I less than equal to n I plus plus. We can simply count the number of times 0 plus equal to I equal to rule of 0. Oh, sorry, it should be SOE. Okay, what happened was 10 SOE equal to true. Answer plus equal to n I plus plus is I true. This just let me see what is see out of that. Let me see what is 7 because when we try to do 2 with 2 and j is equal to okay, it should be j. Sorry for that. It should be j. Don't put these bundles, of course. It works fine. Let's just try to submit it and see if it works for the rest of the test cases or not. It doesn't because input is 2, output is 1, expected is 0. So why is it that? Because uh, expected was 0 because the number of well 1 is less than, okay, less than that particular number. Concerned about less than equal to, so it's fine. Yeah, it's fine. It's working. And now we can move on to the next question, which consists of reverse integers. So reverse integers is given 32-bit integer, we need to return x, which is reversed. If reversing, x causes the value to go outside the signed 32-bit integer range. This is one key thing that we need to make sure. Otherwise, the question is very easy. When sign equals to 1, if the value of x is less than 0, we can consider it as sign is equal to -1, and then we could just convert x is equal to the absolute value of x, which is possible. After that, what we try to do is we try to have int temp is equal to x by temp is that, and we'll try to reverse it using int reverse is equal to 0, right? We move on to the rev is equal to rev into 10 plus temp modulo 10, right? After this, what we're trying to do is once you have done this, you can say if if the value of rev is exceeding int max by 10, exceeding int max by 10, if it is greater than int max by 10, then we could simply say that yeah, it might contribute to a value which is like which might be greater. So we should take light. We should return 0 for that. So 0. Otherwise, what we'll do, we'll divide this and we'll return if 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 what happens next. Next, if for some reason we're not if sign is equal to -1, sign is equal to -1, we give that particular sign to that number, so -1, and we return that reverse integer. Let's see if it works or not. I think it should work. Okay, it's working. Let's see if it works for the rest of the test cases. -1 to 3, output is 3 to 1, should be -1. Less than equal to sign, search for that. So the problem is happening for this particular integer. This particular output we expected was 0. So the problem is happening for such particular cases. So instead of writing it that if condition over here, I've tried to put it over here, and I simply return ref into sign, right? And let's just see if it works or not. I think it should work. It's let's try to test for the corner cases, right? Okay, for this particular corner case, it's failing. In order to handle this particular test case, I could see because it's an int min. So in order to travel or iterate this, I could feel that if int min x and x is greater than int max, if this is possible, then this should be returned to 0, right? Let's try to copy this and use this particular test case for now. In order to do that, value of rev. So yeah, if I could just do this, edit this condition, I could see that it will only happen till temperature is greater than 0, and won't be working for any other values. Let's just see if it works. I think it should work for the rest of the values as well. Yeah, it's working. So only this condition was missing. This we are doing for checking if the ref consists of that particular integer or not. I'll show you what was the difference which was coming out. Let's print out the temp values and let's just see what were not was not able to get what we're not able to get achieved. So if you just see that if we remove greater than 0 condition, you will see that uh, the temp value is this, right? The temp value, even though it's an absolute value taken, but still the temp value is negative. Here it is negative, here it is negative, and so yeah, as you can see that it's an int min, it's over the int min, but still uh, this value is achieved. So in order to do that, we have put it over here. We have used this particular condition, and in order to use this particular condition, you will see that after this happens, this particular condition happens, uh, when cout temp comes up, then this value is greater than 0 and it's normal division takes place. Normal division takes place. So the negative sign is not required anymore. Normal division takes place. So, like if you just go a little bit further, you would see that uh, we are taking that particular digit. So 8 is taken off, and then this thing is happening. And if you try to divide it by 10, it will result in a positive value and not in a negative value. That's the difference, because we have assigned it that it will take a positive value. Initially, when it is an int min, it cannot take a positive value, because if it takes a positive value, then this becomes greater than int max. So if you take a positive value of this, it will become greater than int max, and you will have to handle that particular condition. In order to handle that particular condition, what we did was we tried to first declare that okay, it would take an absolute value, but if it is an absolute value, then once it gets divided by 10 and gets into the range of that particular element, then it is okay. Then we can say that the negative sign is removed from there. So this is the condition which is actually taking place over here. And it's a great question. You can explore a little bit about it. So yeah, that was the condition. Just don't forget the temp condition. You can just write over the handling overflows condition part. Done. University is done. Using handle overflows. Overflows take positive value of m. Right. Okay. So moving on, when go to the next question, that was Excel sheet column title. So we move on. Here I have already done this particular question, so let me just remove this. And so what does the question say? It's the opposite of what we did yesterday. That is, we are given an integer column number, we return its corresponding column title as it appears in an Excel sheet. For column number 1, we return A. For column number 28, let's just see what is happening in 28. For 28, it is AB, right? It is AB. If I give it 28, then it is AB. So what is happening? So 28, we can write 28 as 26, right? 26 raised to the power 1 into the value of a, and here the value of a is 1, right? Here the value of a is 1, it's not 0, plus 26 raised to the power 0 and the value of b, and the value of b is 2. As you can see some major differences. It's not a 26-bit integer, because had it been a 26-bit form, then the value of a would have been 0 and then the last value would have been 25. It is a shifted 26-bit pattern where the value of a is 1 and not 0, and the value of z is 26, right? So these are the differences which are actually happening here. So when we try to first, like in order to do this, what we can do is we can just write it in a more generalized form, right? So there's a number. What we can write it as 26 raised to the power n. It is a, that particular a character, and that value of a character plus 1, right? A plus 26 raised to the power n minus 1, and this happens again. This happens again, and we take b plus 1. So this is happening, right? Currently this thing is happening. So what we can do, first we try to declare result, string result equals to, and then what we try to do is we are able to see that if it is 28, then first we try to take a mod of it. We first try to take mod of it, right? First try to take mod of it. So while column number, first try to take mod of it. So when we take a mod of it, column number modulo, or it should be like 26 int digit, that particular digit is modulo 26. So the char that would be generated, the char that should be generated would be result plus equal to digit that particular digit. Here in this case 2, here in this case 2, as you can see it is 2. After that we could just simply say that column number so as you can see, if you try to extend this formula, there will be a particular point where the value of 26 is to power 0, and here let's just take a character to be set plus 1, right? So this is n in some form, right? Now what if we try to take a minimum, like we try to have -1 differentiated? So when we try to minus it, what will happen is only this one gets deleted. Only this one gets deleted from here itself. And if we try to take a mod of it, then the rest value goes and we are able to retrieve our character, right? We are able to retrieve our character, that particular character. So for that, I think you should do minus minus column number. Minus minus column number is done. After that, you get that particular character. So in the case of 28, you do minus 27, you get minus 27, you get 27 mod 6, that is 1, and that you could just simply do it this and it would work. You have got your character, and then after that you could simply do column number divided by 26 equal to 26, and after that you reverse that particular string which you've got, that is res dot begin, res dot end, and then you will be all set to return that particular string. So the condition is like it's not an exact what do you call it, 26-bit integer system. It is a shifted integer system. It is a shifted characters based system in order to do that. So you'll have to decrement it, and why we need to decrement it I've already explained over that. Yeah, here's the question. Yeah, we are able to get a solution, so we can move on to the next particular question, that is, so right now we are trying to do questions related to bit manipulation, and this would take very less time compared to what we have already done. So 6 questions are left. The first is, this is a hidden integer array that consists of n non-negative integers. It was encoded into another integer area array encoded of length n minus 1 such that encoded, this is the formula which is given, encoded of I is equal to arr of I XOR arr of I plus 1. If you know the XOR properties, then you are easily able to crack this particular question. So the first, you are given the first value, right? You are given the first value. If array is 1021, then the first is 1, and encoded is, as you can see, encoded is 1s or 0, and then the value was 1s or 0, and after that we had zeros or 2, and then 2s or 1, right? As you can see, this happened. This is the condition which happened. So this is actually happening. So can we just assume, can we just say that the first value of our resulting vector would always be this value vector, we have the vector which we need to return the result. We just go over the solution, we just go over the particular solution, or like we just see a pattern. This is the first variable. This is the first variable, so we are already given the first vector. So we could just simply res dot push back. We can do first. So we know the first vector. We know the first element of our vector, right? We need to return this vector, and we need, using something, we need to return this. We need to make this particular vector. We need to construct this vector, right? And we are returning this. So what we are doing is, I'll just try to make you understand what is the process. So if it is 1, this is 2, this is 3. So what happens is, first is this encoded I is equal to encoded arr of I and arr of I plus 1. So encoded of 0, which is encoded of 0, it should be arr of I 0 and arr of XOR arr of 1. Right? It should happen like that. Same goes for 1, same goes for 2. There should be 1, there should be 2, 2, right? This happens, this happens. Okay, so let me just see if it works or not. So this was the first, this is the first element, uh, the first which is given over here, the first variable which is given over here, right? When we do encoded, the value of encoded is 1, 2, 3, right? So if we had XORed 0 over here, then we could have got 1. And if we would have XORed 2 over here, like arrow of 1, arrow of 0 is 0. If we could have XORed 2 over here, like 0 XOR 2, then we could have got 2. And if we could have XORed 2 with any some variable that is 1, then we would have received 3, right? And we know a condition, right? If A is equal to B XOR C, right? You could easily able to extract Z using A XOR B. You know this, like you know this particular condition, right? So we will use this particular condition that by XORing this and this, you will get this particular value. You are able to get this particular value, you will use this value in order to receive this. You will do 2 XOR 0, you will get 2. You will forgetting 2, you will do 3 XOR 2, and once you do 3 XOR 2, you will get the value as 1. Hence, you are able to construct this array, right? So what we'll do is, we have to do nothing. We'll just iterate through that particular decode encoded variable, and also we need to do this like for int is equal to 0, I less than encoded dot size I plus plus, right? And res dot pushback, res dot pushback. Uh, what we can do is res dot pushback. Similarly, just push back all those elements, right? Res dot pushback. We have encoded I XOR res I. That's it. It would be developing all these. Yeah, it's working. Let's see if it works for the rest of the conditions, for the rest of the test cases. Yeah, it's getting passed. We are able to retrieve this. It's very slow, or like it's maybe the compiler or the time judgment system is very different. Yeah, it's you shouldn't be taking care about this. So yeah, we move on to the next question, which is counting of bits. We have counting of bits lined up. We have sort by the number of bits. We have count the number of consistent strings, and we have sum of all XOR subset totals, and last one being the Hamming distance, right? So we have now started solving questions from the bit manipulation. We have tried to solve all the questions related to maths, and now we'll be solving questions related to bit manipulation. That is also part of the day 4, which we'll be doing. So if you could just see the counting bits, counting given integer, return an array answer of length n plus 1, such that for each I, answer the number of ones in the binary representation, right? So we need to represent the binary representation, and to count the number of set bits, which will be discussed later on, there's a built-in function by the name of built-in pop count. It counts the number of set bits in the time complexity of the order of number of set bits which are present in the n. So we could easily do that, and for that we need to do nothing, but we need to just we will be discussing about that later on, like how to have our own implementation of counting the set bits in a much optimized complexity. For now, we are not going through that. I think I think we'll be doing it sometime later. So res dot push back pop. Okay, so it is built in pop count, and the value will be I. That's it. We need not do anything. We return the result. That's it. Okay, there's a spelling error built in. Count working fine. Let's see if it works for the rest of the conditions or not. For the rest of the test cases, I think it should work. It's working. When this question would arise number of 1 bits, I'll be discussing more about the actual implementation. We will not be using the inbuilt library. Right? At that point, we will not be using the inbuilt library. So this is for tomorrow. We'll be going to solve some questions related to bit manipulation, and that's it. So we are moving on to the next question, which is sort the integers by the number of 1 bits. Again, this is the same thing which is happening. You have to sort the integers in the array in ascending order by the number of ones in the binary representation. And in case of 2 or more integers having the same number, you have to sort them in ascending order, right? So we could just easily use the sort function add dot begin, add dot end, right? And we can make our own comparator function. So we are using making our own comparator function using int a, int b. It should be passed by reference. Make sure about that. And we are using comparator. So comparator over here. Yeah. So what else do we need to require? Return built in pop count of a less than equal to build the same function building one of b, right? uh, just in case if both of them are equal, we need to return a less than b, right? Is the question, right? Return a less than equal to b. Same goes for here, and that's it. We need to return this particular array. Bit manipulation is the questions are quite easy. They're based on a fixed pattern, and if you know all those fixed patterns, then I think that it's better than you know you can easily try to solve all types of all patterns of questions which are available. You know about some tricks regarding that. There are some tricks. There are some medium hard questions based on that. So we'll be also solving that also. And if you know about these tricks, I think like you can solve any questions related to bit manipulation. And it's not a static variable. So what we try to do is like we try to declare a static bool comp. That should do the trick. And so okay, this is r, should be r. Okay, so what's happening, you have to sort them in ascending order, right? 0 1 2 3 4 5 6 7 8. 0 1 2 3 4 8 3 5 6 7. Number of set bits based on number of set bits, right? Oh, sorry, it should be equal to, my bad. That's why you shouldn't copy and paste blindly. After that, we move to another question, which is the count number of consistent strings. You're given a string allowed consisting of distinct characters and an array of string words. A string is consistent if all characters in the string appear in the string allowed. Return the number of consistent strings in the array. Right. So what I can see is some reasons, right? I'm not sure why it is occurring inside the bit manipulation technique. Like this question was present in the bit manipulation area, but it's somewhat related to that. It's somewhat that particular area. All the strings are consistent. So as you can see over example 2, all the strings are consistent, and same goes for the rest of them as well. One of the conditions that I'm currently thinking of, one of the approaches that I'm thinking of is we could have a hash map type of something. We could have a hash data structure. Um we could just make have words on it. We can have AD, BD, triple AV, right? We could just it stores the frequency of such characters, and once it does, we match it with the allowed characters and check if that characters are present or not. I mean, that is one way. We could have easily done that because the time complexity, if you think about the time complexity, I would say the time complexity is won't be an issue because it's 10 raised to power 4. So yeah, that could be considered as an option. Let's try to implement that itself. Rather than doing this, we could think of another solution that we assume that our answer consists of all the words which are possible, right? After that, what we do is we make a boolean variable which consists of present, right? It's a vector of bool present, which keeps a track of all the strings which are all the characters which are present in the allowed string, right? So the size would be 26. Size would be 26, right? It would be 0. What we'll do for char ch loud, what I'll do is I'll try to have present and then ch minus 0 equals to true. Cool. I think this would work fine. What can I do is after that, when I'm already given the size of allowed strings which are possible, what will I do? I'll try to iterate over all the strings which are possible. String str, words, or the words. I go to characters. Char ch, I go to a particular each and every string and check this particular condition, right? If check this particular condition that if not of present of ch minus that particular size, that is a, I do two things. I should do two things. I should first res minus minus, and I should break from here as well because I did not because I've suppose as you can see in the first iteration what will happen. I'll reach AD. The moment I encounter D and the D is not present in the allowed boolean variable, I should break from it and I decrement by res because this one string is not our solution, and that's why we have decremented this result. So we are doing it, we are assuming that all the strings are our solution, and then we are trying to remove those solutions which fail this particular condition of not having a particular character, such as D in this case, we have D in this case, we have this is okay, this is fine, we have D in this case. Similarly, we'll be doing for each and everything. So after that, the resultant that the resultant integer that we present, that will be our answer, right? This will be our answer. Okay, so this was answer. I should change to answer. I think this was fine. This was a me just check if not of present ch minus a. Okay, sorry, it should be a. Works. Let me just see if it works for other conditions as well. Yes, it does. It wasn't a bit manipulation question. I think it might have some concepts related to it, but more or less it's more of a hashing based solution. So I think these type of questions should be present in the hashing section. I have no idea why it was in the bit manipulation section, but okay, it was an easy question, so it doesn't really matter. It was a good question. So we move on to the next question, which is sum of all subsets XOR total. Now, for this particular question, XOR total of an array is defined as a bitwise XOR of all of its elements or zero, right? Or zero if the array is empty. So if the array is empty, we simply have one case that should be taken care of. We simply return zero, right? We are not thinking of that. The XOR total of an array is a bitwise XOR of all of its elements of the array. Okay. Nums 1 3. The nums for example, given an array, return the sum of all XOR totals for every subset of nums. Okay. Subsets with the same element should be counted multiple times. Fine, that's not a problem. So we have four subsets, right? So for each nums we can have 2 raised to the power n maximum subsets possible, right? Four subsets of our empty set, which is 0, then 1, then 3, then 1 3. 1 so 3 is 2, right? And then we try to add all these, and then we get this particular solution. So that means one thing, right? That means one thing. That is 516. Let's see what happens for 516. We have 5, we have 1, we have 6, we have 5 1, we have 5 6, we have 1 6 as a XOR of, and we have 5 1 6 as a total of 2. Right. Now we try to see what is happening for 3 4 5 6 7 8. The sum of all XOR of, so the length of the nums is 12, right? There's one observation. So we try to generate all subsets. In fact, let's see if we try to generate all subsets and try to get all the subsets which are possible and try to sum all of these subsets. Like one of the major solutions which I'm currently thinking of is to generate all subsets, that is 2 raised to the power n, because each and every element has a tendency of not being taken and being taken. So that means for n elements, it would be 2 raised to the power n subsets, and we need to sum all of these. And based on the condition like 12, I think it is possible for this particular algorithm to run. So this is one type of approach that we can think of. We can think of a better solution can be achieved, which is a little bit of it's not that intuitive, but it's based on some observation that we need to do. What can we think of is basically, I could just explain it over here. Let's try to see what is happening, why am I experiencing that. So we were given 516 in example 2, 001. There was 5 was there, 5 value of 5 is 101. And when you try to XOR it, there were some other elements which might be generated. So when you try to XOR 5 0, when you try to XOR these two, it will be 1 0 0, right? When you try to XOR these, it will be 0 1 1. When you try to XOR 1 and 6, it will be 1 1 1, right? So this is something. So there will be an empty set as well. So as you can see, there is one observation. There's one observation that the number of ones which are occurring, number of ones, as you can see, number of ones see, another set that would be generated would be 5 XOR 1 XOR 6, right? That would be 5 XOR 1. This was 5 XOR 1, right? So 1 XOR 6 would be, it would be uh, 1 XOR 6 XOR 5 XOR 5. So this was 5 XOR 5. Okay. I'm missing one thing. 1, 2, 3, 4, 5, 6, 7. There should be an eighth one as well, right? So what will be in the eighth one? Eighth one will be, let me just take care of this. So this was 1, this was 5, this was 6, this was 5 XOR 1, right? This was 5 XOR 1, this was 5 XOR 1, right? And 6 was this. So another one would be generated would be like this, like it would be some like this. It would be 0, 1, 0, right? So as you can see, the number of 1 at every place is somewhat same. As you can see, there's one observation, and that thing really makes sense because uh, here we can see that the 1 bits are 4 in number, 1 bits are 4 in number, 1 bits are 4 in number, and there's a perfect reason explanation to this. So why is this happening? Like, what is the thing? Why this like observation? Why? So what is the current observation based on this? So if we try to observe all these binary numbers of these OR that we are getting from this list, they are basically contributing to a factor. That factor is, if the number of elements are n, then the factor of elements is 2 raised to the power n minus 1. In this case, it is 4 because the number of elements was 3, and 2 raised to the power 3 minus 1 gives us 4. So it will be each of the 1 bits as contributing exactly to 4 times. What is the explanation for this? I'll just explain that. So if we are considering that this nums of the size, the nums arrays has n elements, and out of that there are m elements which have ith bit set, which are present, which have ith bit set, right? So if we have n elements total, right, and m have ith bit set, right, ith bit set. So what happens is, uh, now we are making a subset with the ith bit in a set in its OR, right? So if we have m elements which have their ith bit as set, then that means we need to have odd number of elements with ith bit set, or else if we have even number of bit elements or the even number of elements, then XOR will be 0, right? So we need odd number of elements. So to choose all such elements, a number of ways of choosing m elements out of all these elements with the ith bit not set is 2 raised to the power n minus m, right? 2 raised to the power n minus m. Suppose n minus m elements are those elements which have not their ith bit sorted. Ith bit is not sorted for them, right? Is not set it. Like the ith bit is 0 for them. You can just simply assume that. M bits had ith bit as 1, and 2 raised to the power n minus m had 0. So the number of ways of choosing elements with ith bit set will be what? Like the number of ways that we can make the ith bit set could be, suppose we have m elements, right? We have m elements. So what can be possible cases? Suppose out of m we choose only one. Out of m we can choose only one, that is MC1. Out of m we can choose 3 bit elements that will contribute to MC3. In case we can choose all the odd possible combinations. So if you know this combination, like MC1 plus MC3 plus MC5, this is basically 2 raised to the power m minus 1, right? It is a binomial combination. This is 2 raised to the power m minus 1. So that we get the total number of ways which are possible is basically the multiplication of such elements. Like if you could just see, these were the elements to make the ith, the to choose to make the ith bit not set. We also require such combinations that can make the ith bit as set. So here we are making responsible that this particular thing is making the ith bit set, and this will help us by, because this combination will provide us zero. This will not provide any set bit to us, and when we try to use this combination, we can say that yes, our ith bit will be set. So we need to multiply these combinations. So 2 raised to the power m minus 1 multiplied by this particular factor will be, that is 2 raised to the power m minus 1 multiplied by 2 raised to the power n minus m, simply be 2 raised to the power n minus 1. And hence we could say that this is the factor by which the ith bit set is getting contributed, right? So we could just simply say that if we that somehow if we try to get all the set bits in over the integer array and just multiply it by the factor of 2 raised to the power n minus 1, we could simply say that yes, that would be our solution. So if we try to get the number of set bits, here in this case, for example, if we try to say for 1, 5, and 6, the number of set bits were 1, there were 2, there were 2. Then if we try to sum 2 plus 2, 4, 4, uh, this is 4, this is 5, this is 5, right? After this, we got all our bits, we have got all our like set bits. After that, what we can do is, if we multiply it, if we just, if we just XOR it, if you just XOR it, in fact, if you just XOR it, like to find the final summation, it will be right. So we have two conditions, right? If there is no any value of nums that has the set ith bit set, then we can have 2 raised to the power n subsets will be of that particular form, and they will contribute to 2 raised to the power n minus 1 plus I to the final sum, right? So in order to see like what can we do, what we'll try to do is we try to take OR of all the elements. We'll try to first take OR of all the elements. Now when we try to take OR of all elements, that would lead to some value. So first what we'll do is that we try to take OR of all these three elements like 1, 5, and 6. So that is 0, 0, 1, this is 0, 1, 0. So this should be 1, 1, 0. Sorry about that. This should be 1, 1, 0, 1, 1, 0. And this is 101. This is 5, this is 6, this is 1. We try to OR it. When we get an OR, this will be the OR value which is generated. If we try to multiply it by 4, that is 2 raised to the power n minus 1, then we'll be able to get our answer. Why are we ORing? The major question can arise that why are we not doing any other thing? So in order to OR it, like the basic funda is to check if at least one bit is set at each and every value. So if one bit is set at each and every value, we can consider it as long as at least one bit is set. The XOR of all the subsets that will be produced will lead to generate 2 raised to the power n minus 1 numbers with its ith bit set. So for each and ith bit set, we can say that suppose we know that at some particular point there will be a phase where this ith bit would be set. So that ith bit set will contribute to 2 raised to the power n minus 1 times, right? So it's quite easy. Like when we try to XOR it, we will be getting the actual uh, we are getting the XORing, and after that, uh, what we try to do is we could derive it mathematically also. How we'll try to derive it mathematically? We can call it if there is any value of nums that has the ith bit set, right? If there is any value of nums which has the ith bit set. Now there is an ith bit set, any value of nums which has ith bit set, right? Out of all these elements, then we can call that exactly 2 raised to the power n minus subsets will be formed, right? We can call about that. So they will be contributing to 2 raised to the power n minus 1 plus I times, right? They will be 2 raised to power n minus 1 plus I times will be contributed. 2 raised to the power n minus 1 times will be contributed to the final sum. And if there is no value of nums that ith bit set, we can say that there will be no term in all the subsets that I have a bit set. So we can do one thing. So if we try to see for all those elements that was happening, we could simply call uh, like if you could just see that for two for right. So it will be like for this particular summation, I could see we will be multiplying by the number of times the bit is coming, 2 raised to the power n minus 1 plus I. I will be the index bit value if you are, and here in this case it will be the MSB value. It will be the MSB value. So for that we are trying to do yeah, so it will be 2 plus 1 multiplied by 2 raised to the power n minus 1 plus 1 and plus 1 plus 2 raised to the power n minus 1 plus 0, right? So when you try to compute it, we can take 2 raised to the power n minus 1 as common. When we try to take n 2 raised to the power n minus 1 as common, we have 4, we have 1, uh, uh, we have 1, we have 2, and we have 1. And this will be our answer, 7 into 2 raised to the power n minus 1. So the 7 is basically when you try to OR all of the digits, you get basically when you're ORing all those elements, you're basically checking if the ith bit is present, if there is at least some of the as long as one bit is set, the XOR of all the subsets will produce 2 raised to the power n minus 1 numbers. So I know it's a very complicated explanation from my side, but if you try to read some solutions, maybe over some articles based on that, I think it will help you learn a little bit further on that. So what we are going to do is, this is 0 for int I less than I nums. We can call it sum or equal to I. Once this happens, we can simply do sum. We shift it to n minus 1 times. That is num dot size minus 1, right? When we do this, we are able to get the solution. So we run the code. So this is an order of n solution, as you can see. Currently this is working fine. Let's see if it gets submitted for all the conditions or not. Yes, it's fine. This was a good solution. It had a very complicated explanation, but if you could just see some articles based on that, I think it will help you learn a little bit further. Moving on to the next question, the next and the last and final question of our day 3, we have Hamming distance. Now, the Hamming distance between two integers is the number of positions at which the corresponding bits are different. So we're given two integers, return x and y, return the Hamming distance between them, right? So if you just try to compare the 32 bits, here it is given we have 32 bits. So we can do easily for int I is equal to 0, I less than equal to 31, I plus plus. We can simply just divide each other and check the last bit. If the last bit is same, then we can call it the Hamming distance between the number of positions at which the corresponding bits are different. So if the bits are different, we can simply, you know, say that yeah. It won't be a problem. You could have, you could just simply check if the last bit is seen. If x and 1, right? We have got the last bit for x. Try to compare it with equal to or not equal to. Let's just do y and 1. That means that if the bits are not same, then when count plus plus and we do it till count and we shift it to 1, shift it again to 1, and that's it. I think this is an easy solution. This is the easiest solution that could happen. If you just see for this particular test case getting submitted, let's see for the other test cases if it submitted or not. Yeah, it's fine. It's happening. There are other solutions, of course. One of the solutions is another solution that we can think of is uh, what we can do is simply instead of iterating through order of through all the 32 bits, we can do it in much more easier time. First of all, what we'll try to do, we'll try to XOR. We'll try to XOR. Okay, we'll try to XOR. So value XOR it would be like something. In this case, I could say that if elements are present like 0001, 0001, and 0100, the XORing would be like 0101, right? This would be XOR. So you could easily count the number of active bits, you could number of set bits, right? The number of set bits in the XOR of this, in this particular combination, like this is XOR X XOR Y, the number of set bits in X or Y would be equal to the Hamming distance as well, right? So no need to do this. I think you can easily do that. So return, and that you can use a built-in function, built-in pop count, and instead of we should use n, and this would work fine as well. This will also work fine, right? If you just try to submit it, this would be doing in order of number of set bits which are possible. So order of set bits, this is an order of set bits. This particular function works in order of the set bits which are present. So instead of order of 32, we reduce it to the number of set bits. So here in this case, it will be order of 2, which is still an order of 1 time complexity, but still it is optimal. It is optimal compared to this one, right? So yes, tomorrow we'll be discussing about the total Hamming distance and questions. We'll be more solving more type of question. We'll be also solving this particular question which I'm talking about at the number of 1 bits. Now, why am I saying this is important? There are various ways to do it. One of the ways to do it is just iterating through all the 32 bits. Another approach is to just like write a function that takes an unsigned integer and returns the number of 1 bit, also known as Hamming weight, right? There's a follow-up question also. If the function is called many times, how would you optimize it? How would you optimize it? So the optimization would be done. So that's the part when we'll be trying to have an implementation of our own built-in pop count. And that will be based on a small simple trick. And we'll be discussing about that. So today we try to discuss some questions related to maths, your maths questions. If we try to see progress for now, I think for example, our progress for now it is simple. It is for now it's cool. If we try to see the number of questions that we have done 87 questions. We're not done the premium questions. We're not counting about that. If you're only talking about the algorithms based questions, then algorithm based questions are very less in number, if you know. So right now, I think it's been 3 days of time and we have solved almost 100 questions. So that's a great progress. That's great progress. And we'll be trying to solve more questions related to bit manipulation. So we'll be having more type of questions. If we try to see what type of questions we'll be focusing on, you will just move this section and see the number of questions, the type of questions that we'll be doing. So there are some questions that we've already done. If you just sort it by based on difficulty, there's some questions that have some done, but there are still a lot of questions which are remaining. And I think there are some handful of questions in bit manipulation. So if bit manipulation is done, we could have some questions related to what do you call it? We could have some questions related to hashing. So basic hashing problems could also be added over here. So day 4 would be consisting of some questions related to bit manipulation and some questions related to hash table or hashing, normal hashing, right? So apart from that, we will try to solve all the easy questions first. So that's our particular, like we are just trying to make a base out of it. And once when we try to make a base out of it, then we'll try to solve more better questions, and the better questions are only present over the medium. Medium questions are a lot they are good in terms of conceptual in terms of concepts or in terms of implementations. Both of them are good. So we'll try to solve these questions as well. Apart from that, yeah, so currently you would have seen that I'm not discussing the time complexity of such questions for now because these are very easy questions and the time complexity is generally order of n or order of log n when we are using binary search or when you are computing something as like we're multiplicating by a factor of k every time. So that would be log n. Otherwise, generally it is order of n. So it is only when medium questions or hard questions when arrive, I'll be discussing if time permits. So I'll be discussing to try to get a good solution of that. I'll be discussing the time complexity as well as the space complexity for such good questions. So yeah, that's it for now. I think we have solved almost all questions. So that's great progress for now. We will be back tomorrow with day 4. Then we will try to solve bit manipulation, easy questions, and uh, we'll see hashing based questions as well. Some easy questions on hashing, and if you want to know more about the progress that what are the other topics that we'll be focusing on after hashing, we'll be focusing on binary search, we'll be focusing on sorting, we'll be focusing on basic recursion, and that's the part where we are when we are focusing on recursion. That's a part we will also be focusing on stacks and linked lists and queues. There will be one day based on only questions related to stacks, queues, and linked lists. After that, we'll have one session based on sorting. We'll have one day based on sorting questions. We'll have one day based on recursion. We'll have one day based on backtracking. And once we are done solving all easy questions, we'll move on to the maths. We'll move on to the medium questions first of maths, and then we'll be trying to solve the recursion medium questions. And at the same time, we'll be just shifting a little bit towards solving some really good questions on dynamic programming. So we'll try to explore some 40 to 30 to 40 days of medium problem solving, medium questions problem solving, only medium questions problem solving. As you can see, Medium has around 1,000 problems, so I'm assuming that uh, each day we'll try to solve only 30 questions for now. So at a matter of 35 days, we are able, if we are giving 1 week, I think we are able to solve all the tough questions that are possible and will be able to achieve our target of Leetcode 100%. So that's it for now. I think that's a good trick. And that's it for now. So, yeah, see you guys in the next one. Bye.